Hello everyone, welcome back in the course of higher surveying. Today we are in the second lecture of module 8, that is radar. In the last module we have discussed the geometric aspects of the radar, and in this module we are going to discuss the radiometric aspects of the radar. This is second lecture on radar. So these are the books we have already shared with you, and here first understand the radar equation. In case of the geometric aspects in last lecture, we have assumed that we are getting some responses, what we call impulse response, and based on that impulse response we have defined the impulse response width and resolution and the pixel and so on. If the impulse response is more than 50% of the transmitted signal, then we will accept that impulse response as a reflected backscatter. The question is how to decide that, or how to measure, or how radar, sensor or receiver measures this response or the impulse response. Let us see, there is a radar transmitter receiver assembly. Transmitter is transmitting power Pt, and this is the distance between transmitter and the ground surface, or the distance between the transmitter and the surface of object is equal to RT. Transmitter has transmitted the pulse or the signal in the form of wavefront. So wavefronts are reaching towards the surface of earth like this, and the radius of the wavefront becomes RT. So let us say there is a target, that this target will reflect or backscatter area is AS, and so the power transmitted in a radar pulse is equal to PT. Power received at the ground surface will be PT into GT. GT is antenna gain or the efficiency of antenna of the transmitter. It is less than 1. So what is the efficiency of the transmitter? For example, 100-watt energy is put there. If it finally transmits 90-watt power, so efficiency is 0.9, and that is GT. So the power received at the ground or object is this one. So that power density at range, if I divide by the area of the sphere of wavefront, I will get the power density, that is watt per meter square. Then receiving area on the ground is AS, as we have already indicated. So radar cross section we define like this. Alpha is the absorption of the material. So material will first absorb part of the energy falling on that. Now if this is absorption, so this is reflectivity, and this is again an ideal reflectivity. For example, if absorption is 10%, so reflectivity will be 90%. However, this is an ideal case. Let us say that material has some efficiency of reflecting the energy, and which is GS. So what we call is gain. Here it is called the antenna gain. Similarly, we can say other gain term, which is because of the material here, and it depends on the material. So radar cross section is specifying that if AS is 4 meter square, let us say rho is 10%, so 1 minus alpha is 90% or 0.9, and GS is again let us say 80% or 0.8. So I will get sigma equal to approximately 2.8 meter square. So I can say here that only 2.8 meter square area is reflecting. So the power of backscattered pulse from the target is power density into cross section area. So I get this term here, that is the power of backscattered at the surface area. So now we will see again the surface area is there, and there is a receiver near to transmitter. So receiver has a distance of RR from the surface area. Surface area behaves like a reflector like this. So it is reflecting energy in its surrounding. So as a result, reflected backscatter will travel to receiver in a wavefront form like this. So radius of wavefront is now RR. So power density at the receiver at range R will be divided by the area of the wavefront. So we get finally this term here. I hope you agree with that. That power received at the receiver is this one, that is power density, and then multiply by the area of the receiver. Let us make some assumptions. First of all, we may assume that the transmitter and receiver are located very nearby. So, the distance r or the slant range r for the receiver as well as transmitter to the surface is same. The second one is this one, that area of transmitter and area of receiver are also same, and we design them in such a way that lambda square into g, or I can say gt here, divided by 4 pi is area of transmitter or receiver. So, this is a kind of design consideration we have here. Finally, sigma, radar cross section here. So, we redefine it in such a way that it is equal to sigma 0 A, and where A is resolution cell. Remember, we have defined sigma equal to AS into 1 minus alpha GS. Now, we say that let us define a factor sigma 0 such that this sigma is equal to sigma 0 times A, and A is resolution cell, which is equal to RA into RR. What is the reason for defining sigma? The reason is very simple. I have calculated sigma according to the area AS. Now, I want to do the same calculation for the resolution cell, which could be smaller or which could be larger than the AS. Now, if area of the resolution cell is smaller, then I will take the higher value of sigma 0. So, that sigma is equal to sigma 0 into A, and vice versa is also true. I will take a ratio here called sigma 0, sigma, that is radar cross section, divided by resolution cell here. So, we have done some calculation for sigma area, and now I am going to do the calculation for A. So, there is a factor, proportionality factor here. It should be sigma 0. This factor is called the normalized radar cross section A. It is a proportionality factor here. So, this equation becomes this here, that we have replaced this gt equal to g here, and so we have g square lambda square 4 pi cube r to power 4 and sigma 0 A here, and where A is resolution cell written here. Then this equation, power received at the receiver, is the radar equation here, and that says that how much power has been received at the radar receiver. So, that is radar equation. Now, this power is more than 50% of the transmitted one, then I will accept it as a backscatter. Otherwise, I reject it, saying that there could not be any object, or the object is so far away that we are not interested to measure it. This equation of the radar is similar to the LIDAR equation, but the terminologies are quite different here, and that is why we have included it here. Now, in the backscatter, we have two components. One is coherent component and one is incoherent component. What is coherent component? If all the photons in the reflected backscatter are in the same phase, it is a coherent backscatter. Otherwise, if they are in different phases, it is called incoherent backscatter. These concepts of coherent and incoherent comes from the physics, and it is applicable to all remote sensing techniques. The coherent backscatter corresponds to the specular reflection. What is a specular reflection? A particular directional reflection or reflection in certain direction. It is called specular reflection. The incoherent backscatter corresponds to the diffuse scattering, that is, scattering happens in all the directions. For example, like this. That means from a given surface, power is reflected in all the directions because they are incoherent. And this is the characteristics of the incoherent and coherent backscatter. The side-looking airborne radar can deal with coherent as well as incoherent. However, in this whole lecture series of radar, we are only talking about the coherent backscatter. So, please note it. So, even we use synthetic aperture radar, we use side-looking airborne radar or side-looking space-bound radar, we are talking about only coherent backscatter. We have realized one thing here, that we have defined a 1 minus alpha into sigma. So, then we have defined sigma here, and then we say that it is equal to sigma naught into A. And what was sigma naught? We say that it is normalized radar cross section, because it was equal to AS into 1 minus alpha into GS. And this factor 1 minus alpha is nothing but reflectivity. So, reflectivity is affecting the backscatter from the surface. You can see in the whole equation, in this term, PT is the power transmitted, A is the resolution cell, G square antenna gain, lambda generated by the system, r is the distance. So, we do not have any control over the r as well as the sigma 0, or I can say the reflectivity 1 minus alpha. So, now we should understand that how this reflectivity changes or affects the brightness or the response or the backscatter. So, let us understand that what is the concept of the reflectivity and how do we characterize it, in a sense how does it affect the backscatter signal. In order to understand that, let us define the intrinsic reflectivity sigma naught here, and it is the mean reflectivity per unit surface area of material under stimulated conditions. First of all, I am defining this term so that I can measure the reflected response or reflected backscatter at the radar receiver. These terms are basically used for the radar receiver. This depends on the characteristics of the material and the observed radar signal. That is a theoretical definition, but in reality, how do we measure it? That is more important. We measure it by reflectivity estimate sigma hat naught. So, it is derived from the brightness estimate from the calibrated radar sensor and processor. So, remember we are defining these definitions for the sensor. Now, how do I really measure it on the ground surface? So, what do we define it there for the ground or terrain? So, we define quantity sigma naught. It is an average reflectivity of a material sample normalized with respect to the unit area in the horizontal plane, and it is sometimes called the scattering coefficient. Remember, we call it the sigma naught in the last equation in previous slide, that is the normalized radar cross section. Now, we are saying it is scattering coefficient when we are measuring it on the surface of the terrain. We have the gamma, which is an average reflectivity of material sample normalized with respect to the corresponding area normal to the slant range. That means, this is one area here which is normal to this line of sight, and this another area on a horizontal one. So, if I draw the area vector, it is like that, and this area vector is like that. So, I am defining gamma based on this area vector for this area, and I am defining sigma naught for this area vector. So, this is range resolution dr, and this is incident angle theta I. This is x direction or the flying direction, and this is dx, which is azimuth resolution Ra. So, this is dy, which is a resolved factor of dr. So, I can write here dy is equal to dr upon sin theta I here. Similarly, this one is dz from here to here. So, dz is dr upon tangent of theta I. Let us define these areas. One is along the flight direction, or it is on the level plane. So, this dx dy, so it is dx time dr by sin theta here, and over this area if I calculate the average reflectivity, I define the term sigma naught on the ground surface. Now, if I reduce dx dy, I can make a point also, but going smaller than the resolution cell is meaningless now. Similarly, the inclined area is dx into dz. We define the gamma based on this thing. That means average reflectivity on this area is gamma, and average reflectivity on this area is sigma naught. After defining this theoretical idea, let us see what are the factors that influences the reflectivity. The first is the terrain surface roughness, then we have the local slope of the terrain, then we have geometric arrangement of the reflectors or the scatterers, and then we have dielectric properties of the surface material. So, basically these are the four factors that influence the reflectivity of the material on the surface of earth. That means, how do they respond to the incoming radiation of the radar, and so it generates the backscatter. Higher the reflectivity, higher the backscatter, and more reliable response we get at the sensor. So, now we are defining the terrain surface roughness in terms of its undulations. Let us say the ground is like this. So, because of this, average undulation is dh. So, this is reflecting surface also. If this is the wavefront, so lambda is wavelength. So, wavefronts are approaching like this. So, as a result, this wavefront which is here has approached terrain point first, and it is reflected in direction A. Similarly, when this wavefront has further proceeded, it has interacted with other part of the terrain which is at slightly lower elevation. So, like this. So, it is reflected towards B. Now, if I measure the angle theta I here for this point, let us say point A and point B here, let us say B1 on A1. At point A1 we have theta I, and at point B1 also we have the same incidence angle. We say that the surface roughness is devised by this factor called delta phi here, and it is given by 4 pi times dh by lambda into cos theta I, and it is called the Rayleigh criteria. If delta phi is small, we call it the specular surface. Further, if average deviation in the elevation is less than lambda divided by 8 cos theta I, it is called smooth surface, else it is called rough surface. Smooth surface gives specular reflection and rough surface gives diffuse reflection. Diffuse reflection gives incoherent component, but we take only the coherent component into consideration. Specular reflection gives the coherent component. So, in case of specular reflection, reflection will be higher, or the reflected response or backscatter power will be higher. Now, coming to the slope of the terrain, we have defined here the angle called incidence angle. If you zoom it here on this place, real terrain is like this, and we can see here that this is the slope of the terrain here, and this is indicated by the local slope. This is incoming radiation here, and this is the normal of this slope. Now, this angle is called incidence angle of the radiation. So, how does it make a difference? We get some kind of phenomena called a specular point. What is a specular point? When this theta local, it becomes 0. What does it mean? That means, let us say this is the incoming radiation and surface is perfectly normal, and so the normal of the surface and incoming directions are coinciding, and as a result whatever radiation comes here, that is reflected back completely, and this is called the specular point. So, it depends on the combination of the incoming radiation and the surface slope. When it is coming like this, or the line of sight of the radar signal is perfectly normal to the local slope, what will happen? It will be reflected back, and this surface will be appearing as smooth surface, and this backscatter will be very high, and it creates the specular point. In case of small local incidence angle, I get high reflectivity because I get high backscatter, and that is the effect of the specular point. Third one is the geometric arrangement. According to geometric arrangement, we have two terms. One is called the cardinal effect and another is called the Bragg scattering. So, let us look into the cardinal effect first. It occurs when geometric arrangement of the sensor as well as terrain is such that the wavefronts are coming and they are kissing the surface. This is surface which is quite horizontal, and it is another position I am defining. So, this is wavefront which is curvilinear surface here. So, that is a difference between the wavefront and the surface. So, this makes some difference, and if that difference is less than certain threshold, I will say that surface is behaving like a smooth surface, and this effect is called the cardinal effect, and it is shown here because of the cardinal effect. If delta r is less than lambda by 8 as shown here, this is delta r here, this distance. Similarly, this distance on this side will be delta r like this. So, if delta r is less than lambda by 8, a length which is giving you the coherent backscatter, and this is given by lambda into r. So, if lambda is higher, what will happen? The coherent length over which I will get the coherent response will be higher. Similarly, if my range or the slant range is higher, automatically wavefront at larger distance will be behaving flat, and that is the reason this effect will be more visible there. That means, I will get more length on the material surface that will behave as a coherent length. Next is the Bragg scattering. Bragg scattering is another phenomena that is also coming from the geometric arrangement of the line of sight as well as the terrain features. And this is the line of sight here. Features are like this, and after that there is another feature like this, and these features are so arranged that they are exactly at the 0.5 lambda. This is also 0.5 lambda. So, all these features, this feature, this feature and this feature will provide the coherent backscatter, and this phenomenon is called the Bragg scattering. And notice that this arrangement is again by chance. So, it is geometric arrangement that is occurring because line of sight by chance is falling in such a direction that wavefronts are touching or they are interacting with the terrain surface at 0.5 lambda. So, in this case the delta RB is given by n lambda by 2 times of incidence angle. So, if we select lambda accordingly, I can expect the Bragg scattering provided line of sight is in favor. Now, for microwave applications we generally take n equal to 1 here in this case. So, now you go to ground, try to measure this thing. If you find some periodic placement of the features and if you select appropriate lambda, you can expect the Bragg scattering. The last property is the electromagnetic properties. Here we have some dielectric properties of the surface material, and that is some electromagnetic properties of the surface material. Here we see that material constants, magnetic permeability, radiant frequency and dielectric constant of the material that play a role. So, what is dielectric constant? It is the response of the medium to the presence of electrical field. That means, if there is an electrical field around that, what will happen? It will respond, and that response is called the dielectric constant. In this equation, if you see here, small epsilon c, its dielectric constant or complex permittivity. Or it is called dielectric constant of material. That epsilon is the permittivity. Then we have sigma. Please note, it is electrical conductivity. Then omega is radiant frequency here. What about this epsilon 0? It is permittivity of free space. Free space means vacuum. And then we have epsilon, that is relative dielectric constant. This factor is called relative dielectric constant, and this epsilon double dash is the loss part of epsilon dash. So, now we can see this tangent delta term is ratio of the loss to the relative dielectric constant of the material. If loss is higher, what will happen? Tangent delta will be higher, and that will become good conductive material. On the other hand, if I want more reflectivity of the material, what should happen? The material should not absorb or material should not allow the radiation to pass through it. It should reflect it. If that happens, epsilon double dash will be very, very small, and as a result tangent delta will be less than 1, and that is called high reflective material. And if the material is good conductivity of the electricity, what will happen? It will allow the radiation to pass through it, and in that case tangent delta will be close to 1 and I will have low reflectivity. So, such material will give me less reflected backscatter in case of radar. But if there is a low conductivity material, what will happen? It will backscatter more. So, this criteria is given by attenuation constant alpha and the penetration depth. So, this is the relation where c is the speed of the light in the air or vacuum and c is the light in the medium, and 1 upon penetration depth is this term. So, you can calculate up to what depth the radar signal will penetrate. So, for low loss material in remote sensing, it is given by this term, which is an approximation here. For a high loss material, high loss means electrical conductivity is more, and as a result the incoming radiation will be absorbed or passed through by the material, like seawater. Seawater is saline water, so it allows the flow of electricity through it. So, the penetration depth is skin depth only. That means the radar radiation will interact at the skin, slightly reflected, and that low reflection will be just able to tell some depth of the surface, and that is called the skin depth, and which is given by this delta CON, and it is 1 upon alpha, which is approximately equal to this one. One more thing, that phase constant, although we do not use it, but still for the sake of completeness we are telling that phase constant is given by this formula. So, for high loss material I have beta equal to this much, and for low loss material, that means high reflectivity material, is beta is this much. And we have seen that how the reflectivity of the material influences the brightness or the backscatter towards the radar receiver. Now, let us look into again the same aspect. That means we have measured the reflected backscatter from the radar receiver. What do we observe there? Because we want to convert that backscatter into the image form, where we will have the position, as we told in the last lecture, that each pixel will tell the position. I can say that the complete footprint will be divided into many elements. Each element is 1 pixel, and 1 pixel will be having 3 data. One is brightness, one is location, that is the incident angle, and the slant range. So, that's total 3 data are there in each pixel. So, we have noted down by radar equation that what is the time of flight. Secondly, whether a signal we have received it or not. If we have received a signal, that is if the reflected backscatter is more than 50% of the transmitted one, we say that yes, we have received it. Then based on that reflective backscatter, we say that how much is the brightness level compared to the other one, and that is what we call the calibration process. But before that, try to understand the noise in the data. The noise in the radar image is called speckle. The resolution cell contains the large number of scatters. So, within one cell we have many scatters or reflective objects. So, that return echo from the scatters is coherent, as we have already discussed. We are considering only the coherent component. If we sum up this coherent component, because they are linearly connected or they can be added linearly, what will happen? The brightness has 2 components. One is imaginary, one is the real one. So, we add all the real ones, we add all the imaginary component, and finally we will get some final resultant. Now, assume that there is some noise. The speckle is also contributing to my signal. So, there is one main signal, around that there is some noise. This summation and this summation will give the resultant one. So, because of the noise, we have some extra radiation in each pixel, and that is called the speckle or noise, and that will contribute some higher value of the brightness. And how to remove it, we should now consider it. So, first of all, what is speckle? So, if I take the algebraic summation here of the real component and imaginary component, I will have the final magnitude is this one, this magnitude, and this is the phase here. So, that one is imaginary component and one is the real component. So, let us say in one pixel we observe all these components, coherent components, and we are summing up them. So, it is shown graphically, and mathematically we sum it like this only directly. It is not a vector sum. It is shown although like a vector sum, but mathematically we do like this. So, it is shown here graphically again that this is a real signal without error, but this is the clutter here. Clutter is the noise. And now, if I add this noise, I will get this resultant, because the component of the noise are bringing this point, and this is the resultant which I observe and not this one. This is original signal, or I can say correct signal. And this is the resultant one which is having noise. So, I hope that you are clear with what is speckle. So, what are the characteristics of the speckle? It is an unwanted random noise, and speckle is friend as well as foe, because it is useful quantity sometimes in terms of image interpretation, and sometimes it is not desired. So, it is kind of, there is a compromise between the two aspects. In order to remove the speckle, we assume that over a pixel, the distribution of the energy or the power is Gaussian, and using that we say that we have gamma filters, Frost filters, Lie filters, and multi-look filters. Here we are considering the multi-look filter in this lecture. So, remember one concept in case of synthetic aperture radar, we said that we are looking a point multiple times from different places, and hence I observe more brightness from there or more reflected backscatter from that place. What is the result of that? I am more confident I'll get more backscatter. So if I take the average, I will have more reliable value as well as resolution is improved. That was the aspect we talked about, the azimuth resolution or using synthetic aperture radar. Now same thing I am repeating here also, that I want to calculate the equivalent number of looks and smooth the image to reduce the speckle. Okay, what do? We take an homogeneous area on the terrain surface. So I should expect from that homogeneous area that each pixel should contribute to the uniform value or the same value. That means if I take the mean of couple of pixels in that uniform area, I should get a constant mean, or there will be minimum variation in the mean value, or I can say the variance of the mean should be minimum. Now if I take the ratio of this quantity A, which is mean of the all pixels brightness value, so instead of that it is complex function, each image is a complex number, it can be negative or positive. We take the square of the magnitude factor and then we take the mean of those square factor for each pixel. You can say that A square plus B square plus C square and so on. So we take the mean. Now for those all quantities A square, B square and so on, we take the variance of those quantities and we call it B. So first mean is A, say A square plus B square plus divided by n number of pixels. Similarly, I find out the variance of square quantities for n pixels again. So then we say that take the ratio of A by B. Now if variance is less for the homogeneous area, I should expect low variance or minimum variance. What will happen? This A by B will be higher. That means I have looked or I have observed that particular point, that homogeneous area, from many points, more than one point. I hope that you got the idea, and that's why since I observed it from multiple points, I have more reliable readings or more reliable observation of backscatter. So now we calculate n equivalent, and using that n equivalent we smooth the image over this n equivalent number of samples or pixels, and this is the way we remove the speckle. So that is the idea about the multi-look filters. So let us say that you have received a radar image and you have removed a speckle. Now you want to calibrate radar image, because the calibration will give that what is the value of digital number at a certain point. Take a reference value. Remember reference value concept? Reference value is an ideal value, or what is the reference that we should understand if this is a given area. That means for a grass I have a reference value, for a stone I have a reference value, for some other material, let us say sand, we have reference value. And this concept of calibration, you can understand it from another example. If you see in the television, there are many washing powder advertisements where there is a dirty shirt and there is a very clean cloth, absolutely white. So absolutely white cloth is reference and dirty shirt is kind of noisy data. So once you go through some process of washing using a washing powder or what you call filter, what will happen? Because of this calibration process, all the noise will be removed and dirty shirt becomes the reference cloth. And still we always know that it can never become the reference or the absolutely correct. After this processing also, whatever output we get, there will be some difference, and that difference we call tolerance. Similarly, in case of radar or any system, when we do calibrate it, we go through some process and we try to compare the reference and the modified input or modified pixel value, and then we say that there should be a tolerance, and that is calibration process. Otherwise, if the difference is more than tolerance, we reject that particular pixel and we say that calibration could not be done or calibration is not appropriate. So here we calibrate for the brightness values, we calibrate for the position, that is geometric property. So calibrate brightness, slant range, incident angle, and finally the phase also. Phase will be required for the interferometry purposes. And in case of brightness, we have two components, as we said, amplitude and phase. So we do it for both. After doing this thing, we have a calibrated image. Then we do the verification. We compare the two measurements in the question. So what is the meaning here? After calibration, we got some values of the image, and then we take couple of pixels randomly and we try to see what is the reference value of those in the real field. Then we compare the two, and if the difference between the observed and the reference is within some threshold, we say that we have done calibration successfully. So that is the idea here of the calibration of radar image. Then what are the factors that affect the image quality? So we have done the calibration process and now we have to define image quality. So we have the two false components, one is signal independent and another component is signal dependent. What is the signal independent? We are saying that the backscatter signals are coming from terrain, so that is signal dependent. It is received at the receiver. So if we have some problem at receiver, that is signal independent. So those factors will be called signal independent at the receiver end. At the terrain end, we call it signal dependent because the backscatter is sent from the terrain. In case of signal independent factors, we take the signal to noise ratio so that we can find out what is the efficiency of receiver. At the same time, for signal dependent, it is caused by the range and azimuth ambiguities. Now, how to quantify image quality? So if you see the impulse response here, which is like this. This is main lobe, what we call the main peak, and these are the side lobes. So side lobes are creating the noise. So if I take the ratio of this main lobe to the side lobe, that will decide quality of image observation or the quality of backscatter. Sometimes this kind of figure is also shown. So this ratio we take and then we take the integrated peak side this ratio in both dimensions of the image. If I measure these two ratios, based on this ratio we say what is the quality of radar image. Then we also define what is the quality of synthetic aperture radar or QSAR, and this quality is defined by NEQ divided by RARR. This is azimuth resolution and this is range resolution. And NEQ we have already explained in the previous slides that NEQ is equal to A by B. You can refer it, what's the meaning here. So if the large QSR, if it's better the image quality. That means if one pixel or one resolution cell is looked at by different positions or multiple positions of the sensor, it is a better image. That's a simple interpretation here. What about the radiometric part? In case of radiometric part, we have two phenomena here. First of all, there should be a certain range over which only we observe the coherent signal. That means there is a limit up to which I can mix the coherent signal. Even signals are coherent, but still there is a limit to mix them. And we decide such limit, that minimum and maximum, and that is decided based on the radar sensor characteristics, and that is different for each and every sensor. Now we have ambiguities also. So we have ambiguities in the range, we have ambiguities in the azimuth, and then we have ambiguities contributed by the receiver antenna and by Doppler frequency. And then we have some phenomena called banding and saturation. What is saturation? Saturation is the point over which even the power of reflected signal is coming, but sensor cannot measure. What is banding? Banding happens in the flight direction where bends are created in the radar image. So that is called banding, and that is also a kind of ambiguity. Now if I measure this time depth of swath TR, and similarly signal Doppler bandwidth is given by this. So system is designed in such a way that in order to minimize the ambiguities, TR into BDOP should be less than 1. So this is the way systems are designed, or in order to maximize the quality of output radar image. Now we also should understand that system characteristics or the hardware characteristics also contribute to the image error or image quality. So first of all, what about the automatic gain, that is receiver gain, that is GT if we define. Any error in that, it will be giving error in the azimuth direction. Then we have sensitivity in the time control. So remember, RR is given by C tau by 2, and this tau is the time interval to travel by the one wavelength. So this is lambda here. In any error in tau will be reflected in range direction or the range resolution. So that is the factor we should also consider in order to decide the image quality. So I hope that you have understood how the radiometric aspects are dealt in case of radar. Once we learn how to do it, we have the radar image, we have some noise, what we call speckle, and then we remove the speckle, then we calibrate image, and then we find out what is the quality of calibrated radar image, so that I can use it for the topographic mapping or any other purpose in higher surveying. Once we get a calibrated radar image, then we should have some reliable properties about ground features. So what are the properties? Size, shape of the features, tone, that is color, contrast, that is a difference in the tone. For example, if I have grass, if I have rock, I should get the difference in the color, and that is contrast in tone. Then with texture, texture is the repetition of certain elements. What is a pattern? Pattern is repetition of the texture. And then shadow. Remember, shadow is very important factor in image interpretation. So we should have all these features reliably expressed by radar image. So I hope that you got complete idea about the radiometric aspects of radar. Here we finish this lecture, and we will be considering the next lecture on the radar grammetry, and that is the 3D topographic mapping using the radar image. Thank you very much.